So it's our great pleasure to have with us today Professor Klaus Blaum, the first speaker for 2021. Professor Blaum did his habilitation in Mainz, and since 2007, he's been a director at the Max Planck Institute for Nuclear Physics in Heidelberg, which is one of the amazing places to do physics, I think, worldwide. And it's a place also that has a long collaboration with Israel. All the scientific collaboration between Germany and Israel started with this institute. And Klaus has been continuing this tradition and has many contacts and colleagues in Israel. He's one of the leading experts in the field of precision mass measurements, which he'll tell us about. And he's won many prizes. Only recently, he won the Lisa Meitner Prize, if I say it correctly. And thank you very much for being with us today.
Yeah, Yoni, thanks a lot for the kind introduction. Let me share the screen. We already tested it before, so now you should see it. It's my great pleasure to give the first colloquium in your series of the Israel Physics Colloquium in 2021. And first of all, I would like to wish all of you a happy, healthy new year. I hope we get the chance to see each other later this year. Usually I'm 2 to 3 times a year in Israel. I have very good friends, close collaborations with many of you, but unfortunately I wasn't able to travel last year, but I hope that this will change soon. Looking forward to see you and to collaborate with you. So my talk is about precision tests of fundamental interactions and their symmetries using exotic ions in penning grabs. With exotic ions, I have specifically in mind radionuclides, highly charged ions, as well as antiprotons, so systems that do typically not exist on Earth, and we have to produce them arbitrarily. At the beginning, I will give a broad introduction in the basics of penning grab mass spectrometry. We'll explain how it works, what our measurement principle is, and what the quantity of interest is. I will then focus in the first experimental part, where I present results on the mass of the building blocks of matter, namely the proton, the electron, but also the neutron will be mentioned, where we have produced world record precision. And then in the second experimental part, where I will provide results on atomic binding and excitation energies and their applications for fundamental physics like dark matter search or test of symmetries. Let me start with an appetizer and to give you a motivation on different fields of applications where fundamental masses play a prominent role. I start with the test of nuclear mass models and nuclear structure studies, and you see here a kind of an artist's view on the nuclear landscape. What is plotted is the binding energy per nucleon, which explains here the so-called valley of stability. These are the black nuclides here. If you go to the left or to the right, you go towards the proton and the neutron grip lines, where the species get less bound. If you go to the upper mass limit, you reach the so-called island of stability, where we search for the super heavy elements, whether there exists this island of stability or not. Another field of application comes from astrophysics and neutrino physics. Neutrino physics, the Q value, which is the mass difference of the mother and the daughter nucleus, is needed in order to check for a finite rest mass of the neutrino, electron neutrino, and the electron neutrino. But also atomic binding energies are of interest, for example, in the study of the different nucleosynthesis paths where we investigate the radioactive species. The last example is to test fundamental interactions and their symmetries, specifically the charge parity time reversal symmetry, but also to measure fundamental constants like the electron mass or the fine structure constant alpha. To give you an example, what I have in mind with testing fundamental symmetries, I show you here an image of Escher, where I assign the dark horse to the particle and the yellowish horse to the antiparticle. So now I start the experiment. You see that both the yellowish one moves to the left and the other one backwards also to the left. Now I would like to apply a symmetry operation, namely exactly at this position here. I hope you can see my cursor, my mouse. I apply a p-symmetry. So I put a mirror there, which is the parity. And I hope you agree that the second image now is now the mirror image. So the right is the mirror image of the left one. Next symmetry operation, I apply the charge conjugation. Well, I use C here for color conjugation because I can't change the charge, but I can change exactly at this position the color. That's what it's going to happen here at the C line. You see brownish goes in, yellowish goes out. Last missing operation, you know it, is the time reversal symmetry, the T operator, which I'm going to apply here at this position. And this let the experiment run backwards. And now if you check carefully, the right image is identical to the left one, except that it's shifted by one row. That's what you see here. This is now the last image, which I've put down by one row. We would call that this is a pi shift. That's exactly what CPT symmetry does. Of course, we do not compare images of Escher. We compare the properties of particles and antiparticles in order to look for a failure of CPT symmetry, which would in fact be a failure of quantum field theory. That's what we're interested in. This CPT symmetry is recognized to be a fundamental property of physics laws that has already been phrased 1954 by Gerhard Lüders and 1955 by Wolfgang Pauli. So this is one of the motivations why we would like to compare the properties like the charge to mass ratio, but also the magnetic moment of particles and their antiparticles. As mentioned, we are mainly interested in the mass of an atom. In fact, it's the binding energy what we are interested in. And the reason for that is that the atomic mass is given by the masses of its constituents. N times neutron mass, Z times proton mass, Z times electron mass minus the binding energy. The reason for that is that Einstein made this famous equation E equals mc squared. So mass and energy are equivalent. Depending on the precision we reach, we can either probe nuclear binding energies, which are in the order of a few mega electron volt over c squared. And in order to probe that, we need mass uncertainties, relative mass uncertainties in the order of 10 to the minus 6 to 10 to the minus 8. So the reason for that is if you have a nucleus of atomic mass 100, that's about 100 GeV. So with a 10 to the minus 6 precision, you reach something like 100 keV. That's sufficient to probe nuclear binding energies. If you would like to test atomic binding energies, they are in the regime of a few electron volts. Take hydrogen, the electron is bound to the proton with 13.6 electron volt. You need a relative mass uncertainty in the order of 10 to the minus 10 and better, because you probe on a GeV scale the electron volt precision. This is about what we are interested in. How do we do that? Well, we store and cool charged particles in electromagnetic fields. For the storage, you need typically a radial force, which can either be by an electric field, by a magnetic field, or a light field. In our experiments, we are solely using charged particles, so we apply electric and magnetic fields, but no light fields. Second of interest is that we would like to relate the quantity of interest, so the atomic or the nuclear mass, to a frequency. The reason for that is that frequencies can be measured at the moment with the highest precision in physics. And in order to do so, we would like to have a kind of an harmonic potential for the storage device, because then the particle oscillates with a very characteristic frequency. It's like a pendulum clock. We only have to count the number of oscillations the particle does and the trapping potential, and from that we can deduce the quantity of interest, in our case, the mass of the nucleus or the atom. Third ingredient is that we cool the particle motion in order to minimize field imperfections. Cooling means damping of the oscillation amplitudes, so the volume the particle probes gets smaller and smaller and smaller. So therefore, inhomogeneities that you might have in your electric or magnetic field are reduced, are minimized, and therefore we can reach the highest precision. What you should take home for today about our experimental techniques is that we have a single ion sensitivity. So all our experiments deal with a single ion stored at the same time. In fact, we have infinite storage times. So I will give an example of an antiproton that we have stored for 2 years, a single antiproton, and we are doing a frequency measurement as the quantity that can be measured with highest precision. Very often, when I give a presentation, I get asked, how do we compare with LHC physics? Because I talked about symmetry tests like CPT. I will also talk about dark matter search. All of that gets also done in high energy physics by particle physics. The difference is that the LHC works at high energy, so typically in the 7 TeV scale, while our experiments get performed in the milli-electron to micro-electron volt regime. So there are 18 orders of magnitude difference in energy, and therefore also 18 orders of magnitude in temperature. The LHC, I would call the energy frontier, while our experiments, I call the precision frontier. However, they are really complementary. So it's really good to have both of them so that one can either probe failures of these symmetries and the interactions either at highest energies or at highest precision. How do we do the storage of the charged particles? Well, we use first a strong magnetic field. In the strong magnetic field, the ion with the charge Q and the mass m reveals an oscillatory motion because the Lorentz force equals the centrifugal force. So by the strong magnetic field, in our case typically 7 Tesla, the particle is forced in this radial plane. But of course it can escape along these magnetic field lines. In order to avoid that and to obtain a 3-dimensional confinement, we superimpose a weak electrostatic potential. Weak because the voltage difference between the ring electrode and the end caps is typically 10 volts or a few 10 volts, so rather low voltage. But that is sufficient to store the particle also in this 3rd dimension. In fact, the ion motion is a little bit more complicated than that what is shown here in this animation. The reason for that is that because of the superposition of the electric magnetic field, the radial motion splits up into 2 motions, a modified cyclotron motion and the so-called magnetron motion, which is an E cross B drift motion superimposed with this axial oscillation due to the trapping potential. So what we have is the ion oscillates with 3 characteristic frequencies, which are in fact harmonic oscillators. A typical penning trap is shown here on the right-hand side. The inner diameter is about 1 centimeter, so it's smaller than a cup of tea. We have the ring electrode, hyperbolically shaped, and the two end cap electrodes plus correction electrodes for an as perfect as possible field adjustment. And there are holes in the end caps in order to inject and to eject the exotic species. The quantity of interest is the so-called cyclotron frequency, given by the charge times the magnetic field strength divided by 2 pi in the mass of the ion. You may now wonder, because this νc is not displayed in this figure here. That is true. However, there is a relation between these 3 eigenfrequencies and the sought after cyclotron frequency, which is called the Brown-Gabriel's invariance theorem. So if you take the sum of the square of the 3 individual frequencies and you take the square root, then you obtain the true cyclotron frequency. So in order to determine the mass m, you measure the cyclotron frequency νc. However, you also have to know with the same precision the magnetic field strength B. That's the reason why we typically first measure a reference, the mass of the reference ion, where the mass is known, for example 12 carbon. By that we calibrate the magnetic field. Then we measure the unknown species. Then we do again a calibration, and then we interpolate to the time when the actual measurement happened and can extract from that the mass of the ion of interest. This is how the experimental setups look like. For example, the one on the left-hand side is the ISOTRAP experiment at ISOL de CERN, where we measure the mass of radioactive species. It's an apparatus that looks incredibly complicated. It's about 8 meters long and 8 meters in height, because you have to prepare your radioactive species, you have to stop them, you have to manipulate them, to clean the ion bunch until the measurement can happen. Here on the right-hand side, you see a penning trap tower where in fact 3 penning crabs are put on top of each other. It's at the moment the world best penning crab mass spectrometer called Alpha Trap, where we have demonstrated an uncertainty even in the range of 10 to the minus 12. It gets put together in a clean room in order to avoid dust particles and so on before it gets installed in the apparatus. This is about the storage, but what about the detection? How do we measure, in fact, the frequency of the ion that oscillates in the trap? We use a so-called non-destructive detection technique so that the particle can still be used after it is detected. And the reason why we can do so is that the charged particle, when it oscillates, it induces a tiny current in the segments of the ring electrode. This current can be picked up with a helical resonator or an LCR circuit. It's an impedance which becomes, in resonance, a real resistance. So we can measure a kind of a voltage drop across this resistor here as a function of time because of this induced image current. The signal is very small, in the order of about 1 femtoampere, but we have developed sophisticated detection electronics in order to be able to measure that. And if you, as soon as you have this signal, you do the Fourier transformation, and then you get your frequency spectrum, and from the frequency spectrum, you can obtain the mass of the ion of interest. The electronics is rather complicated. You see here a toroidal cylindrical coil made out of niobium titanium. So it's a superconducting coil with a very high Q factor, quality factor. You see here low noise cryogenic electronics. It's based on gallium arsenide field effect transistors. It's home built. All of our electronics is home built. You see here a lot of filters and so on in order to be able to detect single particles. That we are able to do so, I would like to demonstrate here with this video. What you see here are the signals of 7 protons stored simultaneously in a penning crab. So this is 1, 2, 3, 4, 5, 6, 7. You may now wonder, all protons should have the same mass. That's true. So why do they appear at different frequencies? So that's the signal as a function of the frequency, the oscillation frequency. The reason for that is that they do Coulomb repulsion. So they are sitting in the same trap, they see each other, they repel each other, and therefore move at different orbits in the traps and see tiny different or in magnetic fields with tiny differences. That's exactly why you see them here. So 7 are too many. We would like to do experiments with a single proton, so we have to remove them. That we do in a kind of an evaporative cooling. So if you have your trapping potential, I hope you can see that. We lower the potential walls until the hottest particles escape, and then we increase the wall again until we remain with a single particle. And that's what is happening now. We remove one after the other. There are 4 in. They get together. Now there are still 2 protons in. Now we remove the second last one. And after this is a real-time video, after about 20 seconds, we remain with a single proton stored in the trap. And already this single measurement would give us an uncertainty of something like 10 to the minus 8 to 10 to the minus 9 in the field. This is how an apparatus looks in reality. It's called BASE, the Baryon Anti-Baryon Symmetry Experiment. It's a penning trap installed at CERN, where we do experiments on antiprotons and protons, among others, for the CPT symmetry test. You see here the superconducting magnet and the 2 cryostats to cool the apparatus to 4 Kelvin and all the electronics that's needed for the detection and the frequency measurement. With that, I would like to do a short break and would like to ask if there are questions. So this was a very broad introduction on our measurement techniques. And before I move on first results of the masses of the constituents of matter, I would like to ask whether there are questions or not. Of course, you could also ask at a later time.
Yeah. So the method of removing them is it just is it with feedback or just automatic? You lower and raise.
Yeah, it's Good question, Joni. So in the first part, what we are doing is we simply lower it. So if that's your trapping potential, like a potential wall, we slowly lower the potential walls, and therefore the particles that sit highest in energy, they escape first. It's really like an evaporative cooling technique. This is without feedback, but you're right. We could also do later on the cooling with feedback. So we pick up the signal on the top electrode, feed it back to the lower electrode, but phase shift it by 180 degrees and feed it back. And by that, indeed, we could go down to well below the 4 Kelvin temperature, typically a few hundred millikelvin. Okay, I don't see any further question, also not in the chat. Then I propose that I continue with the first results, namely the masses of the proton, the electron, and I will also talk briefly about the neutron. This work has been carried out in collaboration with my colleagues here at the Institute, Andreas Moser, Sven Sturm, with a colleague from Riken, Stefan Ulmer, and from GSI, Wolfgang Quinn, and Günter Werth from the University of Mainz. So let me start with the proton. We were interested in how heavy is the proton, and of course you would like to express that in atomic mass units, and therefore the ideal reference is 12 carbon. The reason for that is that the atomic mass unit 1U is defined as 1/12 of the mass of carbon 12. However, we do not use only carbon 12, we use it in the charge state 6+. And the reason for that is that we would like to get as close as possible in the charge to mass ratio to the proton. Proton has the charge to mass ratio of 1 charge, 1 atomic mass unit. Carbon 12 has 1/2 in the charge state 6+. So we use 12 carbon to calibrate a magnetic field. Magnetic field then cancels out, and we can express the mass of the proton as the cyclotron frequency ratio of 12 carbon 6+ to the proton times the mass of 12 carbon 6+. And of course, we have to correct, if we would like to express it in atomic mass units, we have to correct for the missing electrons and the binding energy of the missing electrons. We did so, and we obtained a factor of 3 improved value. So this is now the world best measurement listed in the latest CODATA table with an uncertainty of 3 × 10⁻11. The first uncertainty here in parentheses, 1.5 × 10⁻11, is the statistical uncertainty. The 29 is the systematic uncertainty. What I forgot to mention when I talked about this image current detection technique is that the induced image current acts back on the particle. So it distorts the motion of the particle, and this is called a frequency pulling or an image charge shift. And this needs to be corrected for, but what remains is a certain systematic uncertainty because 12 carbon has the charge state 6, while the proton has only 1. So the shift is different, and therefore it remains a systematic uncertainty of about 3 × 10⁻11. Still, it's the best measurement. My PhD student, Fabian Heiss, who has done the experiment, is also very much interested in science history. So he made the effort and put together this plot here, which shows the relative precision of the proton mass as a function of the year of the paper he found. And there are about 220 papers that have reported on a new measurement of a proton mass, dating back even to the years 1813, where gravimetric stöchiometry was used to determine the proton mass to an uncertainty of about 1%. 1920, around 1920, it was Aston who then developed the single focusing spectrometer, then Matochetsov, the double focusing spectrometer. Already at the time, you were down to relative mass uncertainty of 10⁻⁹. And then it was Demelt, 1980, 1990, with the penning crab, who pushed the limit even further, down to 10⁻⁻. And now with our technique, where we can even do phase dependent measurements, we are now down to about 3 × 10⁻11 with the latest result on the proton mass. We also did an experiment on the antiproton mass in order to compare the charge to mass ratio of the proton and the antiproton. To that end, we loaded in 2 different traps. On the one hand side, an antiproton on the other hand side, an H minus ion. You may now wonder, why did we use an H minus ion instead of a proton? This is your homework. Think about it until the end of the presentation, and then we can discuss it. It's a kind of imbalance where one acts as the reference for the other to calibrate the magnetic field. Remarkable is that the experiment is operated at liquid helium temperature of minus 270 degrees centigrade. The vacuum is better than 4 times 10 to the minus 19 millibar. You may now wonder, how do we know that? Well, as mentioned in the introduction, we had a storage time of the antiproton of about 2 years. And since the annihilation cross-section is known, you can calculate back from that we have only about 4 particles, rest gas particles left in the trap in the volume of a couple of 100 cubic centimeters. So that corresponds to a vacuum of better than 4 times 10 to the minus 19 millibar.
Klaus, we have a question in the chat from Chagai. What would be the magnitude of relativistic corrections?
Very good question. Yeah, thanks. Let me quickly go back to here. Indeed, very good question. So indeed, the relativistic correction has to be taken into account. I forgot to mention that. So the way we are correcting is that we do this frequency ratio measurement at different energies. So we excite purposely the proton to express now in temperature from 4 Kelvin to 8 Kelvin to 12 Kelvin. And then we extrapolate down to 0 Kelvin temperature or to the rest, so that there is the relativistic effect. It would be already at the level of 10 to the minus 9 to 10 to the minus 10, the relativistic shift. So we have to correct it down to the level of about 1%. And that we do by using different excitation amplitudes and different energies of the particle. The same we do, of course, for the proton and the antiproton. So we produce them at the lowest possible energy and then do the comparison at different energies and then extract the correct for the relativistic effects. In the case of the antiproton and the H minus ion, we do frequency ratio measurements of the cyclotron frequency. You see here about 6,000 individual measurements plotted, which have been taken over a period of about 40 days, 1.5 months. And from that, we can extract the charge to mass ratio of the antiproton to the proton. And this is the value. It's minus 1 point, and now comes 11 zeros and the 1 with 69 uncertainty on the last digit. So this is in perfect agreement with CPT symmetry, which is, by the way, at the moment, the most stringent test of CPT symmetry on the baryonic sector. There is, of course, other tests that have been carried out on the kaon system by K0 and K0 bar, already at a higher level, 10 to the minus 17. But if we compare on the energy scale, this one here is even exceeding the kaon system. But here, of course, on the baryonic system. It's not that easy. As you might have noticed, we use the H minus ion. So we have to apply a number of corrections before we can release the result, which in fact we do always in a blind data analysis. So we have to correct for the 2 additional electrons. So the H minus ion is a proton with 2 additional electrons. Their masses need to be corrected for. We have to correct for the binding energy of the first electron, as well as for the electron affinity of the second electron. And the 2 electrons, they like to move in a correlated fashion. So we have to correct for the polarizability effect of this system. And when all this is done in a blind data analysis with a frequency offset, we subtract this offset, then we come up with our final result. And that's the value here, which is an amazing agreement with CPT symmetry. Okay, this was about the proton and the antiproton mass. I also mentioned in the introduction the electron mass. This is by far more complicated because the electron is a factor of 2,000 lighter than the proton, so there is no good mass reference that can be used to calibrate the magnetic field. It's simply the relativistic effect, and one of you asked it, is so strong that we could not do the experiment with a single stored electron in the trap. However, we can use a different system, namely a single electron bound to a nucleus. This is, for example, the case for 12 carbon 5+. carbon has 6 electrons. If you remove 5, you remain with a single one, which is also called a hydrogen-like system. This single electron has now an interesting feature, namely it is assigned to the so-called G factor, which is the magnetic strength of the bound electron. This G factor can be measured because this value is related to the Larmor frequency, which is the spin precision frequency in the magnetic field. So depending on, so that is called omega L. It's a G factor half times the charge to mass ratio of the electron times the magnetic field strength. This Larmor frequency can be probed by applying radio frequency, and then we look for the number of spin flips that the electron does. How can we determine the spin flip? Well, the axial oscillation of the ion in the trap depends on the spin value. If the spin of the electron is up, the particle oscillates a little bit faster than when the electron is spin down. The reason for that is that we introduce a very strong inhomogeneous magnetic field, and the magnetic moment couples to this magnetic field. So there's an additional force, mu, magnetic moment, times field gradient, dB over dz. So the electron can be in spin up and spin down, and we can probe that by applying the transition frequency. However, there is still the magnetic field B in. Now comes the first part of my talk into the game. So this is the Larmor frequency, the expression for the Larmor frequency. But the magnetic field also enters the cyclotron frequency equation, the charge to mass ratio times B. If we are able to measure both frequencies at the same time in the same position, the magnetic field cancels out. And that's exactly what we are doing in our experiment. We store the ion in the same magnetic field and measure simultaneously the cyclotron frequency as well as the spin precession frequency. We have done so, for example, for the hydrogen-like silicon-28, so that's a somewhat heavier system, because the original idea was to test the predictions of quantum electrodynamics and strong fields. So you flip the spin, you count the number of spin flip transitions as a function of the drive frequency that's given here, and you obtain the so-called spin flip resonance. From this spin flip resonance, we can deduce the G factor. This is our experimental value, and we can compare it to theoretical predictions. QED is the best field theory that works at the moment for the calculation of these quantities of interest like the G factor. The uncertainty in the theoretical value of 17, so this is the 10th digit, is because of nuclear structure effects. The silicon nucleus is deformed, as well as that you have to take into account polarizability effects. The experimental value, which agrees amazingly well, this is, by the way, the most stringent test of bound state QED in strong fields. The uncertainties for the experiment are statistical. The first one, which is given by the width of the resonance. The second uncertainty is, again, the image charge shift, so it's a systematic uncertainty. And amazingly, the largest uncertainty in the experiment is a systematic uncertainty because of the little knowledge on the electron mass. So our experimental value was limited by the knowledge of the mass of the electron. By that, the idea was born, well, why not to study a system where all of that can be done with much higher precision? And the ideal case is 12 carbon 5+. Theory can be incredibly accurate on this system. It's a perfect 6 neutron, 6 proton system. So proton neutron number is identical. Nuclear structure is known. The mass is also known because it's the 12 carbon. It's by definition known. So the idea is born. If we believe QED to be right, we could invert the equation and can extract now the electron mass from the theoretical G factor compared to the experimental one. That's exactly what we have done with carbon 5+. It's a kind of a balance where now on the one hand side is theory and on the other hand side our 12 carbon 5+. We did so and improved the best value by more than an order of magnitude. I like to give the electron mass in units of atomic mass units, because then it becomes a 13-digit number, simply because you add a few zeros here. Still, the relative uncertainty is 2 times 10 to the minus 11. On the left-hand side is the relative mass precision, again as a function of years. You see that in about 5 years ago, the latest CODATA value was at the uncertainty level of 3 times 10 to the minus 10 for the electron mass. And the CODATA 2016 value, it's 2 times 10 to the 2.5 times 10 to the minus 11, 100% determined by our experimental value. So like this, we have measured the proton as well as the electron mass. But what about the neutron mass? Do we also have access to the neutron mass? Well, we do, in an indirect way. Very recently, we succeeded to also improve the mass of the deuteron. And since the binding energy of the neutron and the proton is known, and since we have extracted or have measured already the electron mass, we can deduce now from the deuterium mass the mass of the neutron with a world record precision. And all of that has been published here in these papers. So we hold now the world record on the proton, the electron, the deuteron mass, and as soon as the nuclear structure, so the binding energy is improved, we will also improve by another factor of 3 the neutron mass. I talked a lot about precisions at the level of 10 to the minus 11, which is, to me at least, always very difficult to imagine what that means. So I like to give an easy image on our precision regime by making this comparison here. So what you see here is the Airbus 380, which is the largest airplane that exists. And it has a typical start weight of about 500 tons, which is 5 times 10 to the 11 milligram. A standard stamp has a weight of about 4 milligram. So we would be able to determine the difference whether a stamp has been glued on this plane or not. That corresponds exactly to 8 times 10 to the minus 12, which is our present limit on the deuterium mass. However, keep in mind that this precision we achieve on the atomic scale, and very soon we will improve it even by another factor of 4. That's what I'm going to talk next. So even a quarter of the stamp would be able for us to be detected simply by doing a weighing of this Airbus 380. I see now I break for the second time before I move on, and I see that there are questions in the chat. So
no, someone said that.
Oh yes, I fully agree. Was not a question. I fully agree. We all forgot what planes are for, indeed. But even they are no longer in use, these big planes, in the future. Are there questions? Are there questions at this moment to the mass measurement of the constituents of matter?
Actually, I have a question. You mentioned that the deuterium binding energy is known precisely. Why is this so?
Yeah, thanks for this question. This is known from the diffraction spectrometry using neutron scattering of the proton at the ILL in Grenoble. And from the Bragg peaks, you can deduce the wavelength, the Compton wavelength, at the level of about 10 to the minus 8, which corresponds to for MEV lines, that corresponds to an uncertainty of electron volt. And since we are measuring GeV, we can go down then to 10 to the minus 11. So that's the advantage here. So it's done by neutron diffraction spectrometry. The binding energy is known to the level of electron volt.
Okay, thank you.
I have a question about the G of the electron. So first, all these precisions are amazing, and it makes you dizzy. But I saw your result that it is a little bit below, very little below 2. So I remember G equals 2 is the Dirac theory value. And then I thought the correction was plus alpha over 2 pi, where alpha is the fine structure constant. So I thought the ordinary value is just a little above 2, and you give me a value just a little below 2. So can you reconcile this for me?
Yes, thanks for asking that. The one that is a little bit above 2 is for the free electron. But here you have the bound electron. So in addition to the QED correction, you have to correct also for the nuclear part. And that shifts down the G factor to slightly below 2. So it's not, it's a bound
not
electron.
The free electron.
Yeah, the one slightly above 2, it's 2.002 is for the free electron, where alpha over 2 pi is the first order QED correction. However, for the bound electron, you also have to correct for the nuclear structure, nuclear recoil, nuclear magnetization effects, and that shifts because they have different signs. That shifts the value slightly below 2.
Thank you.
Klaus, can I ask a question?
Sure. That must be Roy.
Yeah. So that fantastic precision agreement between theory and experiment and the G factor of the bound electron, the theory I'm assuming is QED. Can that be used to place bounds on possible new physics? And I mean, maybe in a different way than the free electron G factor measurement can?
Yes, it does. And people are looking into that, whether indeed a difference could be assigned to interaction with new particles or so. Unfortunately, for many of the systems, the largest uncertainty still comes from nuclear structure, which is probably the same that will come at some moment with the isotopic shifts you are doing. I'm going to talk about that next. But people are getting more and more interested in whether we could set new bounds on that. I think there's a paper from Soldan Harman on that and from Marinova.
Okay, thanks.
Okay, with that I move on for maybe the last 10-12 minutes or so to the third chapter, which is electronic binding and excitation energies. Work that we have obtained here at the Max-Planck Institute for Nuclear Physics in Heidelberg with the pentatrap experiment, together with my colleagues Jose Crespo, he's a world expert on highly charged ions, Sergei Eleseev, Yuri Novikov performed the experiment, and the theory that was provided by Moritz Havercourt and Soldan Harman. In fact, two completely different theories. One is bound state QED by Soldan Harman, and the other one is based on many body perturbation theory. It's a kind of a solid state physics approach of many particles that Moritz is using. Since we have demonstrated that we can reach this really high precision, we came up with the idea whether that can be used in order to measure also electron binding energies. The idea is simply that we use a system in two different charge states. And as a test example, we use xenon that has the proton and electron number Z equals 54. So this is the atomic electronic configuration. It's a krypton-like system plus 5 s2 electrons, 4 d10, and 5 p6 electrons. Now we remove once 17 electrons and once 18 electrons, as it is given here. And now by comparing these two systems, their cyclotron frequencies, by knowing the electron mass, we can deduce the binding energy of this 18th electron from the frequency difference of these two systems. That's exactly what we did. So we measured the cyclotron frequency ratio of these two species, xenon 17 plus and xenon 18 plus, with an uncertainty of about 10 to the minus 11, so 1.4 electron volt. And from that, we can deduce the binding energy of this 18th electron sitting in the 4d1 configuration. Experimental value is 432.4 electron volts, with an overall uncertainty in the order of 3 to 4 electron volts. And these are the theoretical values by Paul Indelicato, Soldan Harman, both are QED calculations. And the agreement is amazing. It's really at the level of 1 electron volt out of hundreds of GeV. And that is the most stringent test of many electron calculations that has been done for the first time in such a system. However, this was not the initial idea what we wanted to do. Initially, we wanted to perform mass measurements with applications in neutrino physics, namely by the determination of the endpoint energy. The best example is the decay of tritium to helium-3, where the decay releases an electron and the neutrino. The neutrino takes away a certain energy. However, if you do a Curie plot and you look close to the end point, you can extract the upper mass limit of the neutrino mass, which in fact was recently published by the Katrin collaboration to be below 1.1 electron volt over c squared. And the Q value has been measured by my colleague Ed Myers from Florida State University. We were interested in a second system that can also be used to extract an upper mass limit of the anti-electron neutrino mass, namely rhenium. It is the beta decay with the lowest Q value. It has only a Q value of 2.2 kilo electron volt, around 2.2 kilo electron volt. So we were interested in the mass ratio or the mass difference between rhenium 187 and osmium 187, and we used the charge state 29 plus. One of the advantages of using highly charged ions is that the frequency scales with Q, and therefore the uncertainty goes down by 1 over Q. Of course, what is needed in these neutrino physics experiments is the atomic mass, while we measure ionic masses. So we have to correct for the energy difference in the binding energies of the 29 electrons attached to osmium compared to the ones attached to rhenium. This we need from theory. We have done such an experiment pentatrap. It's an apparatus which uses 5 penning crabs, a stack of 5 penning crabs on top of each other. Therefore, it's called a pentatrap. You see how the sequence looks like. We have in the central trap, we have our osmium ion. In the neighboring traps, we have rhenium ions. And we can swap forth and back between these two. So we can measure always in this trap number 3, and we get once osmium, rhenium, then osmium, then rhenium, and we can measure the frequency ratio. And this swapping gets simply done by changing voltages, and the ion gets pushed forward and backward. That works very reliably. And we reach storage times of days. We can plot the frequency ratio. So the blue one is now the osmium ion, and the sorry, vice versa. Blue is position 2. So that is when the rhenium ion is in. The lower curve corresponds to position 1. That's when the osmium ion is in. You might now argue, okay, you measure at the same position. That's true, but you measure at different times, and the magnetic field might have changed during the time. That's correct. The advantage of this multi-trap configuration is that we can also use this trap number 2 for frequency measurements. And then we measure at the same time because we can use these two as references. And that's what we do then here. So this is now for the same ratios for this trap number 2. Color code is inverted because here we have rhenium in, here we have osmium in. That we do for days and days and days, and then we compare the frequency ratio. What happened with rhenium and osmium was something really extraordinary. Namely, we observed 2 different values. In about 50% of the cases, we obtain a ratio, which is given by this number here. You see this, it's very close to 1 because it's a mass doublet. However, a significant difference, and the difference is about 200 electron volts. In about 50% of the cases, we get a certain value for the frequency ratio of rhenium to osmium, and 50% of the cases, we get a 200 electron volt larger value. We really got puzzled. Then we came up with the idea, okay, what happens if we measure osmium against osmium? We take 2 osmium ions and we always compare them, and we obtained unity, as it should be. We did then the same for rhenium 29 plus against another rhenium 29 plus ion. And here we did not always get unity. Sometimes we got a slightly different value of 200 electron volts. And then we had the idea, the reason for that might be that we have 2 different electronic configurations. There is an excited electronic state in rhenium, which is given here. So the state we were looking at the beginning is a krypton-like structure, and then 10 electrons in the 4D shell. However, there's also a stable electronic configuration having the 4D9 4F1 configuration with an excitation energy of 200 electron volts and a lifetime of about 3 years. So the ion, highly charged ion, can be produced in 2 different electronic configurations, where the lifetime is even years, which is very amazing because it might be possible to use such a configuration as a clock transition. So we measured the difference of these two electronic configurations, and you see here our value. The excitation energy is 202.2 electron volts with an uncertainty of only 1.7 electron volts. So that's 8 times 10 to the minus 12 uncertainty. And we asked 3 different theoreticians to provide us with a value by using different techniques, and they agree amazingly well with our result. And of course, they didn't know the value beforehand. So that is really remarkable. The same we did for osmium 30 plus, which has exactly the same electronic configuration. Also there we found this excited metastable state. And that's now really a neat feature because that allows us to search for suitable clock transitions. In fact, if this transition could be used for a clock, it would improve the present best clock by 6 orders of magnitude because of the long lifetime. The width of the line would be in the range of microhertz. Of course, the energy is unfortunate. With 200 electron volts, it's not a good clock transition. But anyhow, it shows the possibility that we can search now for such long-lived excited electronic configurations. Last topic, that is the probe for new force carriers. And I cite here also Roger Seri, who just asked the question. I know that he's very much interested in, namely doing isotope shift spectroscopy for fifth force search. The idea behind is that one studies the isotopic shift between different isotopes of an element in 2 different transitions. The isotopic shift depends on the mean square nuclear charge radius and the field factor, as well as the mass factor. And that's where the masses of the involved species comes in. If you plot 2 transitions against each other, it's assumed in the so-called King plot that there is a linear dependency between the isotopic shift of these different transitions. Now, not taking nuclear structure effects into account. I know that this might cause a deviation, but taking now first order King plot analysis would give you a linear trend. If we observe any deviation, not me, but the people that are looking into that would observe any deviation from this linear trend, that might give a hint to fifth force, so a new force mediated through a scalar field with a certain mass. That's exactly what people are interested in, to look for such kind of deviation, because here what happens is that you have a coupling to a system with a different neutron number. What is required is the corresponding, to know with sufficient precision the masses that are involved. At the moment, there are 3 systems that look very promising, namely the calcium isotopic chain, the strontium isotopic chain, and the ytterbium isotopic chain. We were interested in whether we can reach the required mass uncertainty of 10 to the minus 11, even on such long isotopic chains. And as a first example, we used xenon. The reason is that xenon is a noble gas, very easy to produce in our electron beam ion trap. It has 7 stable isotopes. 5 of them are even numbered, 2 are odd numbers. So we simply use that as a test case. So we measured xenon 126 against 128, 128 against 129, and so on. So all stable species against each other. We were even able to measure for the first time directly xenon 126, which has an abundance of only 1 per mil. Of course, we used here an enriched sample, enriched to about 2%, but still was possible to do so. And this is our result. We were able to measure all of them at an uncertainty level of below 10 to the minus 11. We improved the best values on the most abundant species by a factor of 4 to 7, and the one on the least abundant species by more than 3 orders of magnitude. So our uncertainty is given here by this blue bar, and the literature uncertainty is given by this magenta dot and error bars. So it's a dramatic improvement in these uncertainties. So by that, we have demonstrated that we can measure long isotopic change. For example, in the case of calcium, that will be the first one that we are going to, no, probably we'll address first ytterbium, and then provide these mass values to our colleague doing high resolution laser spectroscopy, like, for example, Roy is doing it. With that, I'm at the end of my presentation. I hope I could show you some amazing results in the field of precision penning grab mass spectrometry, even on exotic systems like highly charged ions and antimatter. It has opened up many new fields of research. I covered the topics of strength test of bound state quantum electrodynamics to test of CPT trim symmetry, as well as the masses of the constituents of matter, proton, electron, neutron mass, and so on. And with that, I would like to would like to express my gratitude to all my division members that have produced the results, and also you for the invitation and the attention. Thanks a lot for joining this colloquium. Thank you very much.
Thank you very much. We have time for more questions.
Can I make a question?
Yes.
Thank you, Klaus, for this nice, really amazing seminar. Yeah, this high precision measurements. Look, you mentioned about this fifth force. What kind of symmetry it should obey?
I don't know. I can't tell. Wait, do you know the answer? As said, we provide only the input parameters. I can't tell you.
The method here of looking at king linearity can identify scalar forces. So it's a scalar field. It's as symmetric as it gets, I guess. The assumption. So here is Gilad saying there is no symmetry in this case. Unlike parity violation or permanent dipole moment, we're not differentiating the coupling to this particle by the fact that it breaks some symmetry that QED respects. It actually respects all the symmetries that QED respects. It's a different trick, if you like, to try and differentiate the effects of QED from the interaction with this field.
Right. My second question would be about that terms that you use to correct the mass. You consider the atomic polarization, right?
Yes.
What is the order of magnitude of it? Do you remember?
You're referring to the to this here. Yes.
Yeah, this
okay.
one.
So the proton mass is in the order of 1 GeV. The electron mass is 1/2000 of it. The binding energy is in the order of 13 electron volts, so that would be a 10 to the minus 8 correction. The electron affinity is in the order of 1 to 2 electron volts, so that's a 10 to the minus 9 correction. And the polarizability is in the order of 10 to the minus 9 to 10 to the minus 10 correction.
Thank you.
Significant. That's absolutely significant.
So we have Kobe and then Michael Powell. So Kobe's son.
Yeah, hi. I would like to ask you about trapping neutrons. I mean, your device was based mainly on magnetic field. Neutron has a magnetic moment. And the question is whether you can use this combined with light or I don't know what to trap it so that one can measure more precisely the electric dipole moment of the neutron.
Good question. We thought about that. But at some moment I decided that I will only deal with charged particles. They are much easier to handle than neutral particles. But you're right. In principle, one could do it. You have to, yes, it would be possible. I don't know whether you could improve things like the mass or the lifetime also, but it has been demonstrated, like anti-hydrogen has been trapped in a magnetic trap. So in principle, it's possible.
Thank you.
Professor Paul, if you want to.
Can I have a question?
Yeah.
I wanted
and Naftali, maybe Michael Paul, he raised his hand first, and then you.
Yeah. Okay. I'm sorry, Klaus. This is a detail in this amazing presentation of measurements. But in the xenon series, I noticed you avoided xenon 130. I was curious. What is there? Is there a reason?
Oh, no reason at all. You're right. No reason at all. Why didn't we do that? No, you're right. We didn't do xenon 130, but there was no reason for that.
All right. Okay. Yeah. Thank you.
Absolutely right. We could have done the same.
Thank you.
Yeah.
Okay, Naftali, I'm sorry I stopped you. You can ask.
I want to ask a more general question. do you have plans to extend these measurements to some other effects or notions like, for example, just someone mentioned the static dipole moment in atoms, or which is related to time reversal violation and things like that. Since you have this fantastic machinery and ability, so
yeah. So at the moment, thanks for this question. So at the moment, we are more interested in if we would push the precision further, and just now we are running an experiment on a G-factor measurement at the level of 8 × 10⁻13 in highly charged ions. That would allow us, for example, also to probe hadronic components. So far, if you test QED, it's always electron-positive, virtual creation of electron-positron pairs. If you would push our limits by another factor of 10, we even could probe hadronic components, like the virtual exchange of pi plus, pi minus, and so on. So this is one regime that we really would like to go further into that. The other system what we are interested in is we are interested in the muonic, in the magnetic moment of the muon. In principle, our technique could also be applied to the muon. Of course, it's much, much more complicated. On the other hand, having demonstrated 10⁻13 now, we could waste 5 or 6 orders of magnitude in the precision and would still have a world record measurement on the muon. Obviously, it lives only a few microseconds or so, but in principle, it's doable. So that would be a totally different technique by storing at the beam facility a muon in a trap and looking for the magnetic moment of the muon. You know that there's at the moment a discrepancy, the so-called muon problem, where the G factor is off by, I think, 3.5 sigma or so. And so that is one other field we are interested in. We don't plan at the moment to go into the EDM field. Yeah, not foreseen at the moment.
yeah, thank you.
Okay, before someone raises his hand, Maol, do you have another question? If not, maybe let's thank this Klaus one more time for this amazing talk.
Thanks a lot, Yoni, for organizing it, and thanks a lot to all of you for joining.
Really amazing causes.
Yeah, thanks a lot. Thanks a lot. And
really amazing. Pleasure. Well done job.
Thanks a lot.